Okay, now let's introduce cubical representation. First, let's consider two-dimensional cube. Let's map a function of two variables x1, x2 on two-dimensional cube like this. For 2D cube, there are two variables x1 and x2. The coordinate x1, this x1 is 0, x1 is 1, x1 is 0, x1 is 1, okay, in horizontal axis, and vertical axis is x2 value, namely x2 is 0 at here, okay, and x2 is 1 at here. So for example, this function, the value of function is 1 when input x1, x2 is 0, 1, 1, 0, and 1, 1. So we can represent this function by select this vertex and this vertex and this vertex. Okay, so we can write as the set of vertex 0, 1, 1, 0, and 1, 1. Okay, where 0, 1, 1, 0, and 1 is coordinate. Okay, value of x1 and x2. And now let's define it. Okay, if we join two vertices, okay, for which label differ in value only one variable or only one bit. For example, this vertex and this vertex different only one bit at here on value of x1. So the edge that combine between 0, 1 vertex and 1, 1 vertex, we write it as x1. X means it may be 0 or 1. Namely, it not depend on the value of first coordinate variable. So it depends only on second variable, namely x2. Okay. Similarly, this vertex is 1, 1. This vertex is 1, 0. Different one bit at here. So we can define edge, okay, to connect between this one and this one by write it as 1x. X mean this variable, okay, not affect the value of the function. So for this example, we also we can select this one, this edge 1, x1, and this edge 1x to express or to represent the function like this. Okay, which corresponding to the logic function. This term is 1, right? This term is value of x1, so we can write this x1 and not depend on x2. So there is no x2 in this term. And this one, x1 can be both 0 or 1, okay, not affect the result. So there is no term of x1 for this. And this one, the value of x2, so you can write the expression as x1 or x2 that can make the function to be 1. Okay. And for this 3D cube, there are 3 variables. Okay, this exists for x1, this exists for x2, this exists for x3. Again, we have vertices. For 3 variables, then there are 8 vertices. And vertices that different 1 bit will have 8. Connect them together. For example, this vertex 0, 0, 0, this vertex 0, 1, 0, different 1 bit. For x2, okay, x2 is different. So the edge that connect between this vertex and this vertex can write as 0, x, 0, 0, x, 0. Okay, and this edge x 0, 0 mean that it's linked between 0, 0, 0 or 1, 0, 0. Okay, between this 0, 0, 0 and 1, 0, 0, and so on. Okay, if the function is min term, this is 0, 2, 4, 5, 6. So it's this point. 2 is 0, 1, 0. 4 is 1, 0, 0. 5 is 1, 0, 1. And 6 is this one. So this function you can write a set of this vertex, right? Or you can select, for example, this edge, and this vertex, like this. Also, you can select this edge that cover this vertex and this vertex, this edge which cover this vertex and this vertex, and this one. Okay, like this. Or you can also select this one, and this edge. Okay. So like this. And if you select this plane, namely it cover this vertex, and this vertex, and this vertex. Note the 4 vertices, the value of those variable, or in this case this is this variable x3, right, is all 0. Okay, and for the first 2 variable can be 0 or 1, right? So we can write it as x0, okay, which cover or include 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0. Okay, this xx mean it can be 0, 0, 0, 1, 1, 0, and 1, 1 for xx. So that means you can select this and maybe select this one. Okay, like this. Okay. So if we want to implement the function with the lowest cost circuit, maybe we use this expression, which you can write as because x3 is 0, then you can write x3 prime, or this one 1, 0. 1 is value of x1, so is value of x2. So you can write it as x1 and x2 prime. Okay. Another example for 4-dimensional cube. For the cube, there are 1, 2, 3, 4 variables. For example, the function we want where the value of x1, x2, x3, x4 is 0, 0, 0, or 0, 0, 1, 0, or 0, 1 1 or 0 1 1 0 and so on. Okay, so we want to implement the function with lowest cost. Maybe we must select this cube. This cube is x0 x0. Namely, this plane cover these 4 vertices with the second and fourth variable are 0 0 0 0. Okay? And the first and third variable can be 0 0 0 1 1 0 and 1 1. That means it's not depend on the value of x1 and x3. Okay, so for this one, you can write the term of x2 prime and x4 prime. And to complete the function, you should select the vertex to cover all vertex that give one output of the function. So if you consider this vertex, and this vertex, and this vertex, so you should select this one, okay, which is 0 x 1 x, and this edge, okay, x 1 1 1, okay, which cover 0 1 1 1 and 1 1 1 1. So you select from this, so you can write it as what? This value of x2, this one is x4, so it's x2 prime and x4 prime plus x1 prime and x3 plus x2 and x3 and x4. Okay, that's all. So you maybe see that it's convenient, right, to write in with this representation. Okay, you need not to write in sum or product term. Okay, that list, okay, the value of input variable, okay, that make the function to be 1, and for some variable that not affect the value, maybe it can be both 0 or 1, you write it as x. Okay, and for the n-dimensional cube, and the cube that have dimension 4 or more than 4 is called hypercube. And for n-dimensional cube that has for n-dimensional cube, that means there are n variables. So it has 2 to the power of n vertices. 2 vertices are adjacent if they differ in the value only one coordinate or only one variable, which connect together by edge. And because there are n coordinates, each vertex has adjacent to n other vertices, right? Because, for example, this vertex is x1, x2, x3, x4, which may be the value of 0, 0, 0, 0, right? If it different one bit, it may be 1, 0, 0, 0. That means this vertices have this edge. And if this bit different at x2, so it may be 0, 1, 0, 0. So the edge connect between this vertex and this vertex. And if x3 different 1 bit, so it becomes 0, 0, 1, 0. And you can write edge ring connect between this vertex and this vertex. And the last one, if x4 different, so the cube is 0, 0, 0, 1. So you can dot the edge, okay, connect between this point and this point. So this is the meaning of this one. And okay, vertex. Okay, vertex is the cube of the lowest dimension of 0. Namely, it is called 0 cube. Okay, vertex. For example, the value of x1, x2, x3, x4, maybe it's 0, 0, 0, 0, but it's called 0 cube. For edge is one, its dimension is 1, okay, so it's called 1 cube. And for this one is 2 cube, okay. And for 3-dimensional cube, it is called 3 cube, okay, and so on. Note that if you write this one for 0 cube, the value may be 0, 0, 0, okay. For edge is maybe 0x 0, 0, okay. This is 1 cube. It obtains 1x, which may be 0 or 1, okay. And if you write 0x 0x, if there are 2xx, this means it's 2 cube. And if there are x and some constant 1, for example, it's xx1, this one is 3 cube. So the number of x, okay, show the number or size or dimension of cube. For example, if there are kx, so this is k cube. Okay, now let's go to the method for minimize the function. And this one is called tabular method. And we will use the cubical representation. By the way, again, to minimize, we use combining theorem, namely x and y plus x and y prime, or x or y prime in front of y, then the result is x. So it's the same, right? This part is opposite or different. The result will be this one, okay, only the same part. Namely, the function depend on only value of x, not depend on value of y. Okay, y can be 0, y can be 1, okay, both. And the function give the same value, okay, depend on only x. So, for example, if the function f is 1 when the value of x1, x2, x3, x4 is 1, 0, 0, or 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, and 1, 0, 1, 1. So to combine cube, based on this combining theorem, you just find out the pair that the value different only 1 bit. For example, this one. So you can combine this together to 1, 0, 0, okay, and not depend on this variable. You write it as x, okay. And this one also, okay, 1, 0, 1, 1, 0, 1, the same. This is 0, this one is this is 0, this is 1, okay. So if you consider these two terms, so the value based on the only this 101, not depend on the fourth variable value. So you can write it as 101x. And furthermore, if you consider this one 10x, 10x the same, right? But this one is different. 0 1, okay, different one bit. So you can combine these two terms together to 10x x, okay, the same part 10x 10x, and for the different position you put it by x. So from this you can write down the function in the product term of x1 and x2 prime. Okay, now and this is the basic idea, okay, to combine for two terms in cubical representation. Just find out or compare, okay, if two value different one bit, you can combine them together. Okay, now for the procedure of theorem method, there are two steps. The first step to generate a set of all prime implicant, okay, generate all prime implicant. And the second step is to determine the minimum cover, okay, by using minimum cost subset of prime implicant that cover all minterm. Don't forget that your result must cover all minterm, which the function is 1. And for this one, you should find essential prime implicant, which must be included in the final cover, okay, or final answer that you want to know, and remove dominated row from the cover table, remove dominating column from the cover table. Okay, let's see example. Okay, example, if the function is and if the function become 1 when the value of x1, x2, x3, and x4 is 0, 4, 8, 10, 11, 12, 13, and 15. Okay, that you find minimum cover. Okay, how to find it? At first, you should list the function. Okay, list the input from minterm that you want the function to be 1. For example, this 0. If you write it in binary form, it becomes 0, 0, 0, 0, right? And 4 is 0, 1, 0, 1, 0, 0. 8 is 1, 0, 0, 0, and so on. The list 1, you separate to the group, okay, by grouping by consider number of 1. For example, this group, there is no any 1. This group, there is 1, 1. This group, there is 2, 1. And this group, there are 3, 1. Okay, 1, 2, 3. Okay, and this group, there are 4 ones. Okay, that means this group, number of 1 different only 1, right? This group and this group, okay, adjacent group, number of 1 of this group is 1, number of one of this group is 2, so different only one. Okay, now that mean when you compare the value in this group and adjacent group, it's possible to find only one bit different. For example, when you compare min term 0 to min term 4, different one bit. That means you can combine this min term and this min term together. So it become what? 0, 0, 0, the same, it's the same part. It's different, 0 and 1 at here, so it write 0x 0, 0. Okay, and when you compare 0 to 8, this one also different one bit, so you can write x 0, 0. After that, you compare this group and this group. Okay, the element in this group 4 compared to 10. Okay, this is not okay. And 4 to 12. Okay, different one bit. So you can write x 1, 0, 0. Compare 8 to 10. Different one bit. So 8 and 10. X at here. 8 and 12. Different bit at here, so you can write it here. Okay, do this and compare this group and this group elements, and you will obtain result like this. After that, you compare this group to this group again. Okay. Oh, one thing, when you compare the min term that you select or you check mark that already select or be reduced to another cube. Okay, now compare this one and this one. Compare this term and this term. Okay, it cannot combine together. When you compare this term and this term, cannot combine together. Compare this to this. Can 0 x 0 0 x 0 0 x 0 0. Okay, the same, right? Different, only one position. Okay, only one bit. So you can combine them together. Then check, and become x at here, and copy the same part. Then become x 0 0. This one also. Okay, so 8 and 0 8. This one the same, right? With the same part and different at this position. So it's x 0 0. Okay, to be this. Then if you select this one to combine together, don't forget to check it. After that, the term that cannot combine to another term, there is no check. That means this term can not reduce. That means it's prime implicant. Okay, it is prime implicant. Okay. This one also prime implicant. Okay, because you cannot reduce number of variable. Okay, understand? Because for example, for this one, if you write in product term, you can write it as x1 prime and x3 prime and x4 prime, right? There are 3 variables, and for this one, you can write it as x1 and x3 prime and x4 prime. Okay, 3 variables. When you combine this and this together, then it become what? Become x3 prime, x4 prime. Okay, you can reduce number of variable. So this term is not prime applicant because it can be reduced number of variable. But this term cannot. So the term that cannot reduce variable, it is called prime applicant, right? So now you list all prime applicant. Okay, there are 1, 2, 3, 4, 5, 6 prime applicant. Okay, namely this one 10x0. Okay, and this term 101x. Okay, and so on. Okay, for convenience, let I define prime applicant of this term in P1 and P2 for this, P3 for this, P4, P5, 6, and 6 for this. Okay, respectively. Okay, now the first step. Okay, now you obtain a set of prime applicant. Okay, you can generate all prime applicant. Okay, this is the first step, right? Generate the set of all prime applicants. Okay. The second step, okay, this means the minimum cover. Okay, let's consider now from problem we want to make the function become 1 for the value of the input of minterm 0, 4, 8, 10, 11, 12, 13, 15, right? And now we obtain prime applicant P1 to P6, okay, with these values. So now the objective to define the function must cover all of these minterm, right? Okay, to make the function become 1 for this input value. And note, if you want to cover this minterm or this minterm, you must use this prime applicant, right? That means this prime applicant is essential prime applicant. Okay, you must use it. So it's essential to use. That means if you use this term, if you use this prime applicant, that means this minterm 0, minterm 4, minterm 8, and minterm 12 already choose or selected, right? So, okay, to make it easy to process the next step, that you draw the new list or a new table by reduce or remove this column, okay, this column and this row. Okay, because you must use this one, right? When you use this one, you need this minterm already select, so you can ignore it. So now you obtain the new table with the left minterm that you must be select. It is 10, 11, 13, and 15. And prime we can now, there are P1, P2, P3, P4, and P5 that can be selected. Okay, which one you should select? At first, let's consider this and this row. Note, if you select P5, that means midterm 13 and 15 will be selected. So if you select this one, that means you need not to use P3, right? You need not to use P3. So you can remove this row. We said P5, okay, dominate P3. That means you can remove this dominated row, okay, P3. Similarly, for P1 and P2, okay, P2 dominates P1, so you can remove P1, okay. P this row is dominated row, okay, by P2. Namely, if you select P2 to cover this midterm and this midterm, that means you need not to use this P1, okay. So you can remove this. After remove, you can write a new table like this. And from this, you note that to select midterm 13, you need to use this one, right? Namely this P5. Okay. Then when you select P5, that means midterm 15 also be selected. Okay, this one also, okay. If you want to cover this midterm 10, it's covered only by this P2, so P2 also must be selected. Okay, finally, when you select this one, delete this, you delete it, and delete the corresponding column for midterm that already selected. This one, okay, this one, and this one, then you remove this column. If you select this one, that means you select this midterm, okay, these two midterm already selected, then you can remove. So now the table become empty, then you can stop the process. Okay, so now for this you select this one, right, as essential prime applicant, and for the last table you select P2 and P5. So your final cover is P2, P5, and P6. Or write that in as it is here, or you can write in sum of product term. This is one, the result you obtain, okay, the minimum cost or minimal sum, okay, expression. Next example, for example number 2. For this example, we want the function become 1 when the input value of x1, x2, x3, and x4 0, 2, 5, 6, 7, 8, and 13. Okay, if you apply this input value, the function will be 1. And for 1, 12, and 15, don't care. Okay, the result may be 0 or 1. Right? And another input output will be 0. So at first step to generate all prime applicant. So we list all of this. Include, don't care also. So for 0, 0, 0, it is 1, right? For 1, it is 1. It's from don't care. 2, 3, no T, right? 8 from this, right? 5, 6, 9, 12, 7, 13, and 15. Again, you group. Group by number of 1. Okay, logic 1. After that, you compare to combine or find out one bit different value from element in it at the same group. Namely, for example, this one different one bit. So you take this one that already combined, okay, together and become this 00x. 0 to this one, different one bit at here, so it becomes this. 0 and 8, different one bit at x1, so x1 is x. Another value is 0, 0. Okay, the same part. After that, you compare element in this group and this group. Okay, 1 and 5, different one bit at here, so you can write x as here, okay, and so on. Okay, now when you do until you cannot reduce, you select this one. Okay, no check mark. Okay, the no check mark is prime implicant. So now you obtain how many? This one also. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, 7 prime implicant. Now you obtain this one. Okay, the second step. Okay, to cover all minterm. Okay, you use this minterm. Okay, note. For this step, you can ignore. Don't care, right? Because the objective you must select of minterm. That one function to be 1. Okay, must be 1. But for don't care set, it can be 1 or 0. So it is not to list in this table. And now let's consider is there some row that dominating row, dominated row? No. Okay, no. Is there some essential prime implicant? No. Okay, no. Okay, now then how to reduce? Okay, note, for example, this one, column 9 and column 8 is 3 check, right? And this one is 2 check. We said this column 9 dominates column 8. So if I want to, don't forget that we must select all of this minterm, right? That means if we select, for example, this term and this term, that means we select this and this minterm, right? Or if we use this one, that means we select this one and this one. Okay, also this one. So that means we can remove this column, right? We can remove this one, because when you remove this one, the left minterm of this column, this one and this one, okay, the prime implicant is this and this. That means if you want to select some prime implicant, maybe P4 or P6, that means you select this one, it also cover this minterm 9. If you select this one to cover minterm 8, it also cover minterm 9. So you can remove this, okay, and left only column 8. Okay, Similarly, for column 13, 3 checked, and column 5, 2 check. Okay, this column dominate this column, so we can remove this dominating column because if you remove this one, the left check at here, so you must select this midterm, right? That means you must use this term or this term. Okay, this prime implicant or this prime implicant. If you select this one, you also cover it also cover this, right? It also, if you select this, it also cover this midterm that removed previously. So now you can delete this one, you can delete this one, okay, and become this table. After that, you can find out if there's some dominated row or not, okay, or some essential prime or some dominating column. If yet, you can remove it. Okay, so from this one, we find out, find something. Oh, this one. Okay, 2 check it here, 1 check it here. So P5, okay, is dominated by this row P7. That means you can remove this one. What else? This one check at here and 2 check at here. So you can remove this one. Okay, then you can reduce, okay, size of table. And again, you repeat this process. Okay, and this one check it here. Okay, 2 check it here. Sorry, for this one, this is 1 check, right? At the column, you must select midterm 8, and that is already this 1 check. That means you must select P4. If not, you cannot cover this midterm 8. Okay, you must use this one. So if you choose this one, that means you can delete this row and also this column, because if you select this term, this midterm and this midterm already selected. Okay. This midterm also 5, only 1, right? Covered by only one this P7. So you must select P7 in order to select this midterm 5. And when you select P7, that means you also select this midterm 7. So you can delete this, and this. Okay. But the result is you left this P1, P2, and P3, and row midterm 2 and 6. Okay. Again, from this, if you will see that this row, okay, is dominated by P2, then you can delete this one. P3 is dominated by P2 also, so you can delete this one and become this. And now this midterm that is already this prime implicant, so this prime can become essential now. Then you select this one. Okay, now after you select this one and remove this, it's become empty table. Then you can stop the process. So now you select this, right? and what else? This and this. So the final cover, okay, is P2, P4, and P7. Okay, P2 is what? P2, 0, 1, 0x10. So you can write it as this one 0x10, and P4 x0, so x, P7 x1 x1. So you can write the expression like this in minimal sum. So it's x1 prime, x3, x4 prime. Okay, this one. x2 prime and x3 prime, x2 and x4. Okay, this is minimal sum of the function. Okay. Okay. Example 3. This one. For example number 3, midterm set, don't care set. You can repeat the process. Okay. If you find out the set of prime, you can resolve. It will come like this. Okay. This. Okay. I skip the detail. Okay. You can repeat or practice by yourself. And now there are 1, 2, 3, 4, 5. Okay, 5 prime implicant. Which must be cover these 4 midterms. Okay. So now let's consider: is there some essential prime implicant? No. Dominate row? No. Dominated column? No. Oh, cannot reduce. So what should I do? Okay. If you cannot find out any essential prime implicant, dominated row or dominating columns, so what should I do? For the example, note all of these prime implicant, there are 2 constant, right? 2 constant. That means there are 2 literal. Namely, for this one is x1 prime and x2 prime, right? 2 variable. Okay, this is x2 prime and x4 prime, and this one x2 prime and x3. Okay, and so on. So what should I do? Okay, let's do this process. Let me use branching, okay, technique. And you try to do 2 things. The first try, okay, the first time. For example, we will choose, okay, some prime implicant. For example, let I choose P3. Okay, to include to the final cover. Okay, that means we already select this and this, right? That means we can remove this column because midterm 3 and 10 already selected. Okay, by the result, you obtain this one. Okay, this table. From this one, you can select this P1 or P2, one of these, P4 or P5, one of these. So your cover, okay, your final cover can be, select P3, right? P3 and maybe P1. Also you can select P2 also. Okay, P2, P3, and one of these P4 or P5. Okay, P4 or P5. Okay, so namely it can be 4 possibility: P1, P3, P5, or P2, P3, P5. Okay, all of this is minimal cover. Okay, for possibility. Anyway, for the example, I write successfully P1, P3, and P4. Okay, the second try. Let you try to exclude. Okay, exclude what? Exclude this one. Okay, exclude P3. That means we don't use this P3. Okay, remove it. Remove this one. And the left prime indicator is P1, P2, P4, and P5. After that, we just consider we wanted to choose select from this one. If you select P1, okay, that means this term and this term, this min term 0 and 3 will be selected. And if you select P1, then you choose P5. Okay, to cover min term 10 and 15. That means you can complete. Okay, function. Okay, so your final cover is P1, P5. Or you can select P2 and P4. Okay, also cover all of this min term. Okay, this one also okay. P2 and P4. Okay, for example, if you select P2 and P4, P2 is x0, x0, so your function is your function will be x2 prime and x4 prime, and P4 is xx11 plus x3 and x4. Okay, and if you select prime independent P1 and P5, okay, to implement the function, you obtain the result as this example. Okay, that's all for Tibra method. Okay, and the page that show the summarize process. Okay, you can read it by yourself. Okay, next we're talking about programmable logic devices. The first one is PLA, okay, programmable logic arrays. For this one, composed with at first the input with this buffer. There are two output, active high and active low output. Okay, for active low output, there are a circle or inversion bubble at here, and connect to AND gate. Okay. At first, all of these you connect to AND gate, and the output of this AND gate will go to OR gate. Okay, so the function we will write in AND OR, okay, or sum of product from. Okay. And note there's some cross mark at here. That means this wire can be removed or can be cut by something, okay, or open circuit. So for example, for this example, there is 4 by 3 PLA. Mean that 4 mean number of input. There are 1, 2, 3, 4. Okay, 4 input variable. If we use 4 input variable, this AND gate must have 8, right? 8 input AND gate and 3 output. That means you have 3 OR gate. And if you use AND gate, this answer is 6. That means you can implement the function with product term. Maximum is 6 product term. Okay, product term determined by number of AND gate, right? And output of this AND gate will go to this OR gate. So number of input of OR gate, okay, equals to number of AND gate. Okay, now for convenience, okay, I draw the diagram in compact form. Okay, namely this one. If you want to connect, okay, connect this mark will show that this point and this point connect together. Okay, same voltage or same potential. If you remove it, that means it's separate together. Okay, for example, if I want to program the functions output O1 is I1 and I2 plus I1 prime and I2 prime and I3 prime and I4 prime. For I1 and I2, must AND I1, right? And I2. So this point must be connect. This point must be connect. Okay. And this term I1 prime, I2 prime, I3 prime, I4 prime active flow, right? So we use this. Connect this one, I2 prime, I3 prime, I4 prime. Okay. We do this AND gate. So this product term will all together. Then we connect this point and this point. For another point, disconnect. Okay, separate together. So now output O1 will follow this function. And similarly for O2, okay, O2 is I1, I3 prime, I1, I3 prime, I1 prime, I3, I4, I1 prime, I3, I4, okay, and I2, I2, this one, okay. So and you take these 3 output all together, become O2. Okay, for output O3 also, okay, similarly. So I1, I2, oh, the same thing, right? That means you can use this. Okay, you can use this. Okay. And I1, I3 prime, I1, I3 prime. Okay. I1 prime, I2 prime, I4 prime, I1 prime, I2 prime, I4 prime. Okay, and together, and bring these 3 terms from these 3 AND gate all together. Then you will obtain output of O3. Okay, something like this. Just an example. Okay, the next page just show example for programmable array logic device. This one, okay, PL16L8. There are 10 input. Okay, I1 to I10 and 8 output. O1 to O8. Anyway, for this for this output, it can use as input also. So I/O mean it can be used as input or output terminal by this one. Okay, for example, okay, this one is OR gate, right? OR gate, and this one is AND gate. Okay, AND gate. 1 2 3 4 5 6 7 8. Okay, something like this. Output of this AND gate. Okay, connect to enable. Okay, connect to enable control input of this buffer or inverter. Okay, this one is 3-step buffer with output active flow output. So for example, this if you want to output active, the signal from this one must be 1. Okay, then the output from this OR gate will go to output O1. Okay. For IO2, IO3 also, if you want to use this as output, the enable signal at this must be 1. Okay, must be 1. Okay, so the output from this OR gate will go to this output terminal. Anyway, if you want to use this terminal as input, you must disable this by applying 0. That means now this output become high impedance or open circuit. So now you can use this terminal as input. So this input will feed to something and go to this AND gate. And for this, just show you for bipolar PLD circuit. And this one also can be programmed by applying some high voltage, okay, to vaporize some fields to disconnect diode. Okay, this is fuse, and this one is diode. Okay, on this diagram, we will write down this line, okay, to represent fuse and diode. So, for example, if we apply 0 at here, note that this line you connect to VCC. For example, maybe 5 volt. Okay, this one connect to something around 5 volt. That means if your input is 0, so they will turn on, right? They will turn on. When they will turn on, for example, if the silicon diode voltage around 0.7 volt, then this point become logic low. Okay. So if one of these become low, this line will be low. Okay. Below. This line will be 1 or logic high only when you must apply input at here with 5 volt. Okay, all of this 5. The potential on this line then become high. So then it's called this line as AND line because it acts as an AND function. Okay, it will be high if only if the input all of these become high. Okay, and if we include this inverter, then become NAND function. Similarly for this one also, okay, AND line and inverter then become NAND function. That means now you can implement the function by using two-level NAND. Okay, we design based on two-level NAND structure. Namely, for example, if your function is x1 and x2 plus x3 and x4, okay, or you can draw the circuit diagram, something like this, and gate, right, and then all together. This one is x1, x2, x3, x4, okay, they're two level and or, okay, this one is two level and or. Anyway, if I add inverter and here pair of inverter, it should be the same function, right? And I keep, okay, I move this inverter at here and at here. This one also pair of inverter and move to here and here. So now it become NAND, right? Become NAND gate. This level then become NAND, and this one also NAND. Okay, so it become two level NAND. Okay. Okay, so you can implement the function based on two level NAND structure. For this one, we use CMOD, okay, instead diode, because when the diode on, the voltage is quite high, okay, 0.74. But if you use CMOS, lower voltage level for low. For example, this one, this is fuse, this one is CMOS. In this case, we use NMOS. That means the channel, N channel, will be created when we apply high voltage at gate terminal, right? So when apply high, this transistor turn on. That means this point and this point connect together. So this point become 0 volt. Okay. Okay. So if one of these is high, okay, this line become low. So then this line is function as NOR gate, right? Because if one of these is 1, output will be 0. Okay, this NOR function. NOR function also you can treat it as invert input AND. Namely this one and this one is the same function. Okay, this one, okay, this one also NOR function, and then when you invert it, that is become OR. If you apply input with invert of normal input, that means you can cancel this one. So this one become AND, and this one is OR, right? Then your structure and at here and at here and OR at here. So you can implement the function based on the AND OR structure. Okay, that example. Okay, now let's talking about the often used function. Okay, so let's talk to conventional circuit building blocks that often used in digital circuit. The first one is multiplexer or mux. For example, this one, for multiplexer, there is selector signal. To select the input that want to show the result at the output. For example, if S is 0, X is 0, the input at position 0 will be go to the output. In this example, is W0. Okay, that means when S is 0, output function will be W0. And when X is 1, the input at the position 1 will go to the output. So now output become W1. So this kind of circuit is called multiplexer. Okay, to select one from multiple output. Okay, go one from the multiple input to single output. And this position, maybe you treat it as address. And this one you can treat it as data. Okay, data input, and S is control input. It's multiplexer. And this one just show you example of 4 to 1 multiplexer, namely 4 input. That means you must use 2 bits of selector signal. Namely, if selector signal is 00, the input at 00 position will go to the output. If your input is 01, if S0 is 01, so input at this position will go to the output. When S1 is 10, W2 at 10 position go to the output, and 11, okay, this address input will go to the output. Okay, to select, you just apply the value of address, okay, to select the input that you want to go to the output. And if I want to implement multiplexer, what should I do? You must write down equation from this. When S is 00, value of function is W0. When S is 01, output is W1. 10, W2, 11 is W4. So you can write the two tables like this. And from these two tables, you can write down the function in some object form. Namely, if this condition becomes true, S1 prime, S0 prime, this term will be 1. That means, and you want the value of function become W0, then you add W0 to this term. Okay? And this condition 01 is 1 prime S0. If this condition becomes true, your function must be W1. So you add W1 at here. Okay, and so on. Namely, you write minterm for the condition of the selector signal and the value of function that you want to be, okay, and together. Minterm and the value of the function that you want to be. Okay. Then we obtain this. You can draw the circuit diagram for this expression. It's the basic of multiplexer. And for this, just show you to use 2 to one multiplexer to build 4 to 1 multiplexer. Okay, use smaller size multiplexer to implement bigger size of multiplexer like this. Namely, there are two level multiplexer. Each one is 2 to 1. 1 to 2 input, 1 output multiplexer. For example, if S0 is 0, S1 is 0, that means this go to here, this go to here, okay, W0, W2, and when S1 is 0, you select this. Your output becomes W0. If you select this is 0, this is 1, that means you select from here, right? 1. And because it's 0, that means W2, you go to the output. W2. Okay, this one just example also to use multiplexer. Okay, it's very easy to use this one because the first one to use multiplexer, you must think about selector signal, which input that you want to use it as selector signal of multiplexer. Okay, if you decide to use it, okay, the next step is very easy. For example, if you use W1, W0 as selector signal, then you just consider the value of the function. For example, from this table, when W1, W2, W0 is 0, 0, your output that you want to be is 0. That means you must apply 0 at this position. And for 0, 1, 0, 1, if selector signal is 0, 1, bring input from the position 0, 1 to the output, and you want 1, that means you must feed 1 at here. Okay, 1, 0 also. Okay, want to be 1, then apply 1 at here. Or 1, 1, you want to be 0, then apply 0 at 1, 1 position. Okay, that's all. Or if you want to reduce size of multiplexer, you may use something like this. If you use W1 as 1-bit selector, so let's consider when W1 is 0, your function value same as W0. So you can write W0 at here. When W1 is 1, your function value opposite to W0. Then you write W0 prime. That means when W1 is 0, your output that you want is W0. Then apply W0 at here. When W1 is 1, you want W0 prime at here. Then you apply W0 prime at here. Okay, maybe using inverter, okay, to generate W0 prime. Okay, that's all. And this example also. Okay, for the example, if you select W to W1 as selector signal, so when W to W1 is 0, 0, 0, 0, if function value is 0, 1, same as W0. So W0. And when W2, W1 is 0, 1, function value opposite to W0. So W0 prime, 1, 0, opposite W0 prime, 1, 1. Okay, 0, 1, 0, 1 the same. That means you just feed the value W0 at here, W0 prime, W0 prime at here, and W0 at here. Okay, that's all. Very convenient if you use multiplexer. Okay, and for this part, if I use only W2 as selector signal, when W2 is 0, your function is W1 XOR W0. When W2 is 1, your function is X0. Okay, W1 XOR W0 prime. So you just feed. Okay, W1 XOR W0 at here and W1 XOR W0 at here. That's all. And from this circuit diagram, for XOR function, we use this. Okay, from the previous expression. Okay, actually, the multiplexer can synthesize, okay, any logic function, okay, by based on channel expansion theorem. Okay, so for example, this one. Okay, let's consider this element first. This function, there are 3 input variables. If I use W2, W1 as selector signal, so let's consider when W2, W1 is 0, 0, 0, 0, the output of function is 0, constant 0. Then you apply 0 at here. For 0, 1, the build function value same as the build 0. So you apply the 0 at here. For 1, 0, also same as the B0, apply the B0 at here. And for 1, 1, output is constant 1, so it's 1 at here. Okay, now for channel expansion. Say something like this. Okay, channels expansion theorem. If your function have input variable x1, x2 to xn, okay, if you expand, okay, about x1, your function can write in this form, namely x1 multiply cofactor of function with respect to x1 and complement of x1 and cofactor of function with respect to x1 prime, namely if this term, if you apply this, the value this one mean you apply the value of x1 to 1. That means now if your function x1 is 1, what happened? This term becomes 1, this term becomes 0. 0 and anything then becomes 0. So add something, okay, become this. So 1 and this one, also this one, okay, the same. When x1 is 0, this term becomes 0. This term becomes 1. And this term, this function, when substitute the value of x1 by 0. So based on this configuration, we note that you can use x1 as selector signal of multiplexer. So for example, this one, if your function is this one, this is function, and if I apply the general expression about W2, that means your function is W2 prime and function when W2 is 0 plus W2 and multiply function when W2 is 1. This is W2 prime and W2. Okay, when function is 0, when the value of W2 in the function is 0, this term become 1. Okay, 1 and W1, W0. This term becomes 0. This term becomes 0. This term becomes 0. Okay, and for this, you just apply the value, apply 0 to the W2, then it become, apply 1. Okay, W2, 1 at here, 1 at here, 1 at here, and 1 at here. Okay, 1 prime then becomes 0 at here, at this term, and another term then become this. So it becomes this one. And if you select, for example, if you select more input variable that you want to be expand, okay, or use it as selector signal of multiplexer. For example, if you select this one, expand about W1, so W1 prime and function when W1 is 0, W1 and the function when W1 is 1, so become this term also. Okay, when W1 is 0, W1 prime and W0, and when W1 is 1, okay, this term become 1. So now your expression will show with this W1, W2, and together with 4 combination, which corresponding to the 4 combination value of selector signal W2, W1 of multiplexer. Okay, this one. Okay, for the next one is demultiplexer. Okay. For demultiplexer, the input, one input. There is one input, but multiple output. You can select the position or address of the output that you want the input go. For example, if S0, S1, S0 is 0, data input from here, we go to here. If S1, S0 is 1, 1, okay, the input will go to this output. Okay, if your data input is A, when you apply 0, 0, okay, data A will go to Y0, then Y0 become A, and others output is not active, become 0. When you apply 0, 1, 0, 1, okay, the output at the address 0, 1 or Y1 become A. When you apply 1, 0, it will go to 1, 0 or Y2 position, and 1, 1, A go to Y3. So if you obtain this one, actually you can write the equation for each output. For example, for Y3 will be A when input is 1, 1. So you can write it as S1 and S0 and A. okay, for Y3. This one. For another output, also the same. Okay, you can write it with this condition, and the value become A. This is 1 for Y0, S1 prime, S0 prime, and A, and so on. So you can implement the demultiplexer after you obtain these equations. The next one is decoder. And for example, if you want to decode binary input to one out of n, okay, one of n output. For example, for this example, there is enable input at here, enable input, okay, and two data input and 4 output. At first, for enable, if enable is 0, the output will be 0 out, okay, not depend on the value of I1, I0, okay. XX means it can be 0, 0, 0, 1, 1, 0, and 1, 1, okay. Any value not affected the result, okay, give the same result of 0, 0, 0, 0. Anyway, when enable is 1, okay, the output value will based on the value of data input I1, I0. Namely, when I1, I0 is 0, 0, Y0 will be active, become 1. When input I1, I0 is 0, 1, Y1 active, become 1. 1, 0, Y2 active, 1, 1, Y3 active. Okay, the active bit is corresponding to the value of data input. So this kind of output will be active only 1 bit. Form, and this is what is 4 bit. Okay, in general, for n bit, it's called 1 out of n number of bit. Okay, become 1 only 1 bit. So from this table, actually you can write the equation for each output y2, y3, y2, y1, and y0. For example, if you write equation for y0, y0 will be 1 when what? When enable is 1 and I1 is 0, I0 is 0. So you can write y0 is enable and I1 prime and I0 prime. For y1, it become 1 when input is 1, 0, 1. So y1 is enable and I1 prime and I0. Okay. For y2 and y3, okay, also the same. Okay. Like this. Okay. When you obtain the equation, then now you can draw the circuit diagram. Okay, for this. Okay. Note for this decoder, okay, only 1 bit of the output will be active. Okay, now let's show you something about how to use decoder to implement the function. Okay, any function can be implemented by using decoder. For example, from this result, note for this one, enable and this term. Note is all possible combination of input value, right, or minterm. So if you apply one at here, the output of the function will be minterm of this input. For example, when enable is 1, when you apply 0, 0, 0, y0 is 1. Okay, only one case. So you can write y0 as I0 prime, I1 prime, and I2 prime. For y1, when enable is 1, y1 is I2 prime, I1 prime, I0, okay, and so on. So your output now is minterm, right? Minterm. And you know that any function can write in form of sum of minterm or canonical sum. Okay? Canonical sum of minterm. So, for example, if you want to implement function f1 will be 1 at here, 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 and here, right? If you apply a, b, c at here, a, b, c, and enable is 1, so this one, when input is 0, 0, 1, 0, 0, 1, that means y1 will be 1, right? And when you apply what? 1, 0, 1, 1, 0, 1, sorry, 0, 1, 0, okay, 0, 1, 0, output y2 will be 1. So you just bring this term, and y4, for this one, y7, okay, all together. Okay. Bring this 4 term all together, then you get function f1. For f2, okay, let's combine between this and this, okay, namely 0, 1, 1, y3, 1, 0, 1, y5, 1, 1, 0, y6, 1, 1, 1, y7, okay, all together. Then we can obtain function f2. For f3, oh, 1, 1, 1, 1, 1, 1. Actually, you can select this, and this, okay? 7 bit altogether. Anyway, okay, for use lower cost of the function, you can consider this one. For this one, function f3 with 0 when input abc is 0, 0. So you can write f3 as A or B or C, right? Okay. Anyway, your output is some term, so you should arrange by implement, and use De Morgan, and it become A prime and B prime and C prime invert of this. So A prime and B prime and C prime corresponding to y0 and then invert, right? So it's become this function f3. And the last one, f4. For f4, 1, 2, okay, it become 0 when input abc is 1, 1, 0. So you can write f4 by this expression. f4 equal to a prime or b prime or c, and this case, and a prime or b prime or c prime. And then you apply the Morgan, right? The Morgan apply prime it here. So you keep one of these, and then it's become A and B and C prime plus A and B and C, okay, of this invert. So we just all y6 and y7 together and then invert. Y6 and 7 all together and then invert at the output. So you obtain function f4. The next one is encoder. For encoder, okay, it is opposite direction for decoder. For example, your input may be 1 out of n, and output is binary code. Namely, if your input value is I0 become active, your output is 00. If I1 active, your output become 001. If I2 active, output will be 010. I3 active, output will be 011, okay, and so on. So now if you want to implement this function, maybe you observe, for example, y2 and consider when the output will be 1. So output will be 1 when your input I4 active or I5 or I6 or I7. That means you can write equation like this. Y2 equal to I4 or I5 or I6 or I7. Okay. For Y1, Y0 also the same. For Y1, here will be 1 when I2 or I3 or I6 or I7 is active. So you can like the equation for this like this, y1 2 3 6 7. For y0 become 1 when your input is I1 or I3 or I5 or I7. So when you obtain all output equation, then you can draw the circuit diagram. Okay, now based on this equation, what happened if the user apply the input, for example, I2 and I4 and I4 and I2 at the same time? Based on this equation, I2 at here, I4 at here, the result will be 110. 110, 110 corresponding to I6 active only. So that's a problem. Okay. Your output become 6, but your input is I6, sorry, not I6, right? But I4 and I2. So the result should be what? One of the solution may be you must find out, for example, if I4 and I2 active both at the same time. If you decide that output should be shown as I4, namely output should be 100. So in this case, we will apply some priority. For example, if I7 is highest priority and I0 is lowest priority, for multiple input bit active, the output will show for the highest active bit. For example, if I5, I4, I2 active, the result should be 101, okay, with corresponding to I5, with the highest input that become active. That means the first step, you should find out which input is highest priority, right? For example, your highest priority will be 5. That means I5 must be active, and the higher parity must be not active, namely I6 prime and I7 prime. Okay, the highest parity will be, for example, will be 3. That means I3 must be active, and the higher parity I4 prime, I5 prime, I6 prime, I7 prime. Okay, I4 to I7 higher parity bit must be not active. Okay, and so on. So when you know the highest parity, then now you can use the same condition to show the output of the highest parity active bit. Anyway, follow this method, what happens if I apply this bit active? If highest parity is I7 and I0 is lowest parity, so now I5, right, become the highest active bit, right? So output will show 101, okay, corresponding to I5. And now what happens if input active only I0? So output will show 0, 0, 0, right? But what happens if no any input active? This output will be 0, 0, 0 also, okay, based on this equation. No and 0. So output become 0, 0. So what happened? That means when you see the output A2, A1, A0 is 0, 0, the input condition may be no any input bit active or active only I0. That's not good. Why? Because the 3 bit can represent only 8, right? 8 situation. Namely, highest priority is I7, highest priority is I6, I5, and so on until I0. Okay, this one is 8 situation. But if no any active bit, so this is 9 situation. That's not enough for 3-bit output. So you must create more 1-bit. It is called idle. Idle will be active when no any input bit active. So you can write the expression like this: I0 prime, I1 prime, until I7 prime. Okay, this is encoder. And the next element or next circuit that often used is adder. Okay, for adder, for example, if I want to add 1 0 1 0 1 0 1 1 1, for example, and to add together the result, maybe 1 at here, no carry out. Okay, 1 add 1 is 0 and carry out is 1. Okay, carry out. Anyway, this is the result. Sum, right? Result. And this is carry out. This one is carry in. Carry out is 0. This carry out become carry in for the next digit. 1 add 1 add carry in of 0, then it become 0 and carry out this is 1. This carry out become carry in for the next digit. So when you add together, you add this together and add carry out. Okay, then it becomes 0 and carry out again, become carry in of the digit, add together, become 0 and carry out is 1. So note that when you do addition of two values, normally you have for each digit you add these two numbers together and add carry in. Okay, if you do complete this one, it's called full adder. Full adder. But if you add only these two values, not include carry in, it's called half adder. So let's try to implement half adder first. For half adder, we add 2 bits. Okay, 0 add 0 is 0, no carry out. 0 add 1 is 1, no carry out. 1 0 is 1, no carry out. 1 add 1 is 0, and carry out is 1. After that, you just write down equation. Just consider each output that relate to the input with some function. In this case, it's XOR, right? 0 1 1 0. So half sum is XOR between input X and Y, and carry out is 1 when input is 1 1. So and, right, X and Y. Then you can write circuit diagram for this output equation. For full adder, example this one, you add X, Y, and carry in. The result is sum and carry out. 0 add 0 as carry in is 0, no carry out. 0 0 1 result is 1, no carry out. 0 1 0 result is 1, no carry out. 0 1 1 is 0, carry out is 1. Okay. 1 0 0 no carry out. 1 0 1 result is 0, carry out is 1. 1 1 0 0 carry out is 1. 1 1 1 is 1, carry out is 1. Okay. When you obtain this one, you can use K-map, okay, to obtain the equation. And for this one, carry out is K-map this one. And you can select this term, and this term, okay, to obtain equation. When you get equation, so you can draw the circuit diagram. Okay, this is adder. Okay. For full adder, there are 3 input and 2 output, sum and carry out. If you draw the symbol like this, number input will be left hand side and output is right hand side. Anyway, if you draw input and output terminal, maybe this and this and this, so you must add the direction, okay, show direction by arrow, okay, to show this one is input, right, this one is output. And now if I want to add, okay, multiple bits together, for example, if I want to add x3 x2 x2 x1 x0 and y3 y2 y1 y0, okay, add together, we can use 1 bit full adder, okay. For this one 1 2 3, so we use 3 bit, okay, 3 set of full adder. Why connect carry out of this one to carry in for the next digit? This carry out will be carry in for the next digit. This carry out become the next carry in. Okay, so you can implement. Okay, This configuration is called ripple adder. For ripple adder, note because propagation delay time of logic gate, maybe AND gate, OR gate, or XOR gate, so it takes time. Okay, you must wait. The circuit must wait. For example, when you apply this input, you resolve this one and this one. You must wait a little bit. For example, wait, for example, 10 nanoseconds to sure that this carry out is available. Okay, become the correct value. That means if you wait some propagation delay time, for example 10 nanoseconds, and wait here 10 nanoseconds, and wait here 10 nanoseconds, and wait at here 10 nanoseconds. So that means after 40 nanoseconds, you can use this and this as the correct result. So if you add, for example, 16 bit, that means you must wait 160 nanoseconds, right? More bit adder, you must wait longer time. So so this one is not so good for ripple adder. So if you want to make it faster, what should you do? Okay, you should do something like this by using carry look ahead procedure. How? The problem for the ripple adder, you must wait, right? Wait what? Wait carry in from the previous module. Okay, you must wait carry in from the previous carry out. You must wait carry in from the previous carry out. That means if you can calculate the value of carry in from your original input, so it may be able to make the circuit faster to add to show the result. So now I will design this part, okay? The carry generator. Okay. Namely, this carry generator will receive input from the number that you want to add, okay? X and Y. Okay. And then you feed the result to the adder circuit. So how to generate? Based on this full adder table, note carry out. Now we consider carry out, right? If if X and Y is 0, 0, no carry out. If X, Y is 1, 1, carry out must be 1. Okay. So this term, this condition, if X is 1, Y is 1, the carry out will be 1. Okay. So this term is called carry generate signal. In this case, I use G. Okay, G. Gi is Xi and Yi. Anyway, if X, Y is 0, 1 or 1, 0, carry out may be 1 or maybe 0. It depends on the value of carry in, right? If carry in is 0, carry out also 0. If carry in is 1, carry out also 1. Okay, that means if X is 0, Y is 1, or X is 1, Y is 0, the value of carry out will be the same of carry in. It's like this carry in can propagate to the output. So it's called carry propagate signal for this term. Okay, identified as PI. So when you combine this case and this case together, so the carry out will be 1 when this condition become true or this condition become true. Okay. So you can write equation like this. This term is form carry generate, and this term before carry propagate. Or you can write in short expression of GI plus PI and CI. So it's carry in this one. So now carry out or carry in of the next digit CI plus 1 equal to GI plus PI and C. That means you can write this. If I is 0, C1 then is equal to G0 plus P0 plus C0. If I is 1, then it becomes C2 equals G1 plus P1 C1 and so on. Okay, now because Z1 equal to this, then when you substitute this term to this, you can write in this expression G1 P1 and this term, namely P1 G0 plus P1 P0 C0. This term also, because C2 is this one, then you substitute by this term. So you can write this. Okay, and repeat this. From this one, you see that your carry out or carry in of each digit can write in this expression in form of sum of product, right? Sum of product, namely just two level, okay, two level and or, and right, and together, and together, and so on, right, and together, and sum of all of these are put together. Two level, right? Two level and all. And the value of G and P you can calculate, right? You can calculate by this expression. Okay, and all. Okay. This is the first level, and two level for and all. Totally there are three levels. So you just wait for three level logic gate delay. Then you obtain the value of carry. That means if you add 4 bit, 8 bit, or 10 bit, okay, you use the same delay time to generate the value of carries. So it's make it faster. The next topic is compensation function. Some situation, for example, you may have some, for example, you have half adder, some circuit, and you want to implement full adder. Okay, You need not to design a new one. Okay, you sometimes you may use or apply, okay, a variable circuit, but you need to adjust a little bit to obtain the desired output. For example, assume that you have got a half adder circuit and you want to implement full adder circuit. So what should you do? In this case, you obtain half adder circuit, or called sub-circuit that already available, and you need to design some compensation circuit, okay, to convert the result from sub-circuit, and sometimes maybe use some input to get the desired output. For example, this one. If your sub-circuit is half adder, so half adder, that means you have in your input is maybe x, y, and carry in, something like this, and output is S1 C1. Output is S1 C1. Sorry, C1, and the final result we treat as full adder S2 C2. Sorry, S2 C2. So I want to design this compensation circuit. What should I do? This example, I treat this bit as one input, and this one is this is as output. Okay, one output, and this one also the output. So you just find our equation for this and treat this 1, 2, 3, 4, 5 as input parameter. So let's consider this one. The output S2 will be 1. Will be 1 when your input SY carry in S1 C1 is 0, 0, 1, 0, 0. 5 variable. If you use K-map, you draw 4 by 4 to set of 4 by 4 K-map. For this set, current is 0. For this set, current is 1. For example, when your input is 0, 0, 1, 0, 0, okay, current is 1, xy 0, 0, S1 S1 C1 is 0, 0, come 1 at here, carry in is 0, 0, 1, 1, 0, 0, 1, 1, 0, okay, at here become 1, and so on. Okay, if your input is 0, 0, 0, 0, 0, S2 is 0, 0, 0, 0, is 0, okay, and so on. And for the input, now you have 5, right? Namely, 5, there should be 32, right? 32 row, but just read 8, right? You know that value. Okay, for the left one is you can treat it as don't care. Okay, don't care. So you write down don't care for this input value. After that, you just select maybe this term and this term. For this one, S1 is 1. So you can write it as S1 is 1 and carry in is 0. Carry in is 0, carry in prime. And this term, carry in is 1, S1 is 0. So it's become XOR function, right? Between S1 and carry in. Because this term will be 1 when S1 is 1, carry in is 0, or S1 is 0, carry in is 1. Okay, it is XOR function. Similarly, for D2, okay, you just create K-map and then select this term, and this term. For this term is C1, oh sorry, this group together, this, okay, group together. Carrying is different, no carrying in this product term, and C1, okay, C1 is 1, so this is C1. And the left one, this one you must select, right? Then you choose this one. For this one, it is carrying is 1 and S1 is 1. So it's become S1 and carrying. That's all. So when you know this equation and this equation, so you can use the property of half adder. Okay, for half adder, S1 is XOR between these two input. Carry out C1 is between these two input. So to obtain S, right? S2 is X1 and carry in, X1 and carry in. So I apply S1 at here and carry in at here. So this one then become S2. And for C2, C1 or this term. That means you apply C1 or this term. This term maybe is from this, okay, because this is and between this and this. Okay, this is carry in and this one is S1. Okay, that's all. And example 2. If your subcircuit E is a function of this and want to implement function F, follow this expression. Okay. We can write down the key map. At first, there are 1, 2, 3, right? G. There are 3 input variables, A, B, and C. And your function F also based on the value of A, B, C, and you may use output E as input of F. Now I want to know this circuit, right? Compensation circuit. Okay, to generate function F. Okay, now because there are 1, 2, 3, 4 input of this circuit, then I generate K-map with these 4 variables A, B, C, and T. Okay, based on this function C equal to this one, that means T will be 1 when A is 0, B is 1. A is 0, B is 1. it should be 1 1 1 1 at here, right? But from this table, the value of T is 0 at here, 0 at here. But your result in this table is also value of G, right? Okay, G is 1, but this one is 0. It's impossible, right? Some contradiction occur. That means it's impossible to be 1 at here. So you can write here as don't care. Okay, don't care, because it cannot occur. Similarly, for this term, it's B1 when B is 1, Z is 0. B is 1, B is 1 at here, Z is 0 at here. Okay, this 4 cell should be 1 again, because this equation is value of G, but this cell G is 0, so it cannot be 1. So write it as don't care. Okay. Similarly, for another cell based on this equation, it should be what? 0, right? Of this cell, it should be 0. It should be 0, 0, 0, 0, 0, 0. Anyway, this column, the value is 1, 1, right? 1, 1. That means this cell cannot be 0. So don't care it here, don't care it here, 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 and here. Okay, then become this table. And now for function f, okay, I also draw the K-map, right? And because input is from G, okay, one of them input from G, right? G value. The position that G is don't care. Okay, in this table must be don't care also, right? And based on this function, that want to be, right? This function will be 1 when what? A, B, C is 0, 0, 0. A, B, C is 0, 0, 0. Okay, we want it here. Okay, and 0, 0, 0 at here also, but this person become don't care, right? Because this one is don't care. And this term 0, 1, 1. 0, 1, 1. C is 1. Here and here. Here, but here is don't care. Okay, from this. And the last one, 1, 0, 0. 1, 0, 0. This and this. But this one is don't care, and then is don't care here also. After that, okay, you just select maybe this term and this term. Then you can use, okay, this subcircuit and some of this input to implement the function that you want. Okay, from the example, okay, from this K-map, you may use this with this one group together and this, okay, this to obtain the minimal sum also. Okay, and the last topic that you should know is about timing hazard. Okay, caused by logic gate delays. The first one, let's consider this circuit. If I start the input from, based on this circuit, okay, if your input is from this point, is input xy is 1 1 1, okay, 1 1 1. When 1 1 1, 1 at here, 0 at here, 1 at here, 1 at here, all together 1 at here, 0 at here, then output should be 1, right? From this. And what happened if I take input from here to here, namely take z from 1 to 0, from 1 to 0. That means this point, this wire, is become 0 suddenly, right? Because it's connect directly, okay? But this point, if there is some propagand delay of this inverter, it's not 1 suddenly. It wait, right? Wait some maybe nanosecond. So now this input becomes 0, output then becomes 0. 0 at here, then output becomes 0. Okay. After that, when this inverter give logic 1 output, okay, invert from this, then now this output of AND gate become 1, then output become 1. Okay. Okay. So we know that if there is no delay on this logic gate, the output should be constant 1, right? But because of delay of this logic gate, the output change to be 0 for a short period before back to 1 again, like this, 1 0 1. Okay, it should be constant 1. Okay, this is called static 1 hazard. Okay, it should be static 1, should be constant 1. Okay, but it become 0 for a short period. Okay, this is called 0 glitch. Okay, if you want to solve this problem, you should add this term that cover these two cells, namely is x and y, or consensus term. So you can add this one, x and y, and then all together. Namely, when your input is 1 1 at here and here, 1 at here, 1 1 at here, this one, then output is 1. When you take z to 0, it's not affect, right? This AND gate. Output of this AND gate still be 1. Then when you all together, output still be 1. So there's no 0 glitch. That mean if you want the circuit have no any static hazard, you must do this complete sum, not minimal sum. Okay. Similarly, if your circuit in this form, product of sum, to level or and, okay, the 0 hazard, static 0 hazard maybe occur when your input change from this to this, or change from this to this, or change from this to this. Namely, some one glitch maybe occur. Okay, to prevent this, you must add this term, and this term, okay, into your function. And the last one is dynamic hazard. Dynamic hazard is, for example, your input. For example, your input, and when your input change, your output should be changed. For example, should be changed something like this. But because of some delay in the logic gate, your output not change only one time, but change many times. This kind of hazard is called dynamic hazard. For example, if this NAND gate, okay, have propagation delay with this period. So at the beginning, if input x1 is 0, x2, x3, x4 is 1, 1, 1. What happened? 0, 1, then it's 1 at here, is 1, right? B, 0 at here, B also 1, okay? And C is 0, 0, 1, then it's 1 at here, 1, 1, then F is 0. Okay, follow this. And then if input X 1 change from low to high, change from 0 to 1, what happened? For A, when the time pass with its propagation delay, then it change to 0. A change to 0 after this. Okay. And for this one, B also 1, okay, 1, then it is 0 right here. After that, when A change to 0, B change to 1 again. So with this period, then it make C, okay, A change at here, wait for gate delay, 1 gate delay, then C change. And D is from X4 and C. That means when this change, when the time pass with 1 gate delay, D also change. And finally, the output F depends on the value of B and D. Now B change this one, D this one. So when B change at here, wait for 1 period of propagation delay, then output F change. After that, when D change at here, when B change back to here, it make output F change here, and when D change at here, it make output F change at here. So the dynamic hazard occur. Okay, it should change only one time, but it change many times. Okay, to avoid this dynamic hazard, okay, you should make the function by use complete sum. Okay, similar to this static one hazard. Okay, because if you can remove this problem, so this dynamic hazard problem will be not occur. Okay, that's all for today.